the goal here is to kind of build up an understanding of regression and how that actually relates to machine learning, right? So a lot of you have been doing regression since kindergarten, or maybe first grade, but we want to kind of frame it in more of a classical machine learning approach, and see how we can explore that, right? So we're going to start with everyone's friend linear regression. So we're going to do it in pink. So we're going to start with everyone's friend linear regression, and we're going to do it two ways, right? We're going to do it in a closed form solution. And we're going to do it in a iterative optimization technique, which is called gradient descent. Which seeks to adjust the model for a cost function over a training set, right? Ultimately converging on the optimal parameters. And both of these can actually be machine learning approaches, but this is kind of the foundations. Gradient descent is the foundational aspect of machine learning. Foundational ML approach. All right, before we do that, let's take a look at a data set that we're going to code through together as we build this out. This data set's a little bit interesting in that it is the Ames housing data set. And from 2006 to 2010 includes 2,930 entries. And numerous variables, kind of like size of the house, square footage, what the slope of the lot is like, and a number of things that can be used to compute home values. Interestingly enough, in 2008, I bought a house in Ames, Iowa. So I'm in this data set, and we'll show you my house, or kind of the area where my house is, and we'll see if I got a good deal. Fun note also, 2008 was the start of the housing crisis, and I got one of those no money down loans back in the day, and I was one of the last people to go through, like on the very last day. And then when the housing crisis hit the rest of the country, if you look at this data set, and in general, house prices in Ames never dropped. They didn't go up, but they were just perfectly flat the next 4 years. So kind of comes with living in the Midwest. The housing prices are like, yeah, well, we need a house, and it doesn't get adjusted too much. So new page it in. Okay. Another quick way to look at this plot is, or look at this data set, is a correlation matrix. And this just kind of shows you how similar two things are, right? And so if you've never read a correlation matrix, we have lot footage and we have lot footage. So lot footage versus lot footage is 1 because it's very correlated to itself, right? And then we have other things that are not correlated to itself, like year built is not correlated to overall condition, or maybe it's inversely correlated, right? So the older the house is, then the worse shape it's going to be in. And so it's this dark color. Other things that are highly correlated are garage cars. Appears to be highly correlated to garage area. That makes sense. Here's another one. Total rooms above ground is correlated to ground level living area, right? So a lot of one-story houses. Basement bath full is inversely correlated to basement unfinished square footage, right? So if you have a lot of bathrooms in your basement, then you don't have a lot of unfinished square footage. And that's kind of how you read a correlation matrix. We love closed form solutions, right? It's kind of 2.1.1 closed form solutions. And to determine the optimal parameter values to enhance our performance, it's essential to define, some suitable performance measures. We need a cost function to quantify the inequity or the poorness of the fit. For poorness of fit. And the function is, and then for linear models, we use a cost function that calculates the discrepancy between the model's prediction and the actual training, right? So we just calculate function calculates difference between model and data, right? So this involves kind of like we can do this with a least squares linear regression. And so this involves the inputting of your model data into the algorithm and then determine the parameters that best align the model to your data, right? And so in sklearn, this is kind of sk.linear underscore model dot linear regression. And we'll go back to that later. Fun story, one of my PhD office mates, very, 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 very smart guy. After his PhD, he went to work for some data analytics company, and then he ended up at Amazon, kind of doing machine learning. And then talked to him a couple of years later. And some other people asked him, like, what do you do, like, in Amazon? He goes, linear regression, right? Because everything's about making money, and, they're implementing systems. So it's just like a lot of linear regression. It's pretty much all that not all that people want to use, right? But if it works, you really shouldn't be using other things if linear regression works. Not everything needs a neural network, right? So in the context of the Ames dataset, a straightforward cost function is MSE. So we can go mean squared error, and we're going to call that J. And we do that because in just kind of machine learning, often we call our cost function J. We're trying to minimize J, right? And so 1 over M, which is just the number of data points, times the summation of I equals 1 to M of Y hat of I. That's the estimated value of Y for a specific I. That's what comes from our model. Minus Y of I. That's our actual data piece squared. Right? So that is our cost function. for linear regression. Okay. We like to express this in machine learning as something that might look more like this. Mean squared error, which is our function of our capital X, kind of bold X, that's our matrix, of our hyperparameter theta. That just means I want to get my mean squared error of all of my data X, and for that, I need to find my hyperparameters H, which I have termed theta, that help get me the best model, right? Again, I can just call that's the function I'm trying to minimize, and we'll show you a closed form solution, and then maybe next week we'll do a gradient descent solution, and we'll get very kind of deep into the machine learning terminology. We're going to call that J again, and this is just equal to 1 over m summation of I equals 1 to m theta transpose x of I put it in, sorry, there's an open bracket here. I put the I in parentheses because it's a counting I, not raised to the I, but I quickly run out of places around my letters to put all of my subscripts. Minus y of subscript of placement I squared. All right, what you'll notice here is I replaced x, y hat. That was y hat I. And why can we replace it with theta tx? Because this is what gives us our estimate, right? So theta are the parameters that we train. So what we train to find what we have. Oh, I guess we have y2, right? And so if we train theta, right, and we have x, I multiply those together, and I get y of I. And so that's what we're slowly working our way down towards. A good way to think about this is this plot. Right? Feature 1, feature 2, theta 1 intercept, vertical offsets. And we can see our model here, which is the green line. The yellow line is our error. And then we have our linear model, y hat equals theta 1 plus x1 to theta 2. We'll talk more about those subscripts later. We have a vertical offset here, which is y hat minus y. That's our error. And that's what we are trying to minimize. So each observation of I consists of the scalar response, right, x of I, and holds a certain value for predictors, regressors. So let's just go ahead and add up what this entire equation is going to look like, right? So, sorry, let's add up what this entire equation looks like. I can say y of I is equal to theta 1 x of I, and that might be my feature of a model, plus theta 2. Okay, hang on. I want to write this bigger because we need to talk through the nomenclature here, and it is a bit. Okay, so we have y of I. I want my y value. That's what I actually have. That's my data for a particular instance. So in this case, we have a house, right? that make sense? We have one house. We want to find the price of Austin's house in Ames, Iowa. So equals to theta 1. That is a parameter that we are training for. Does that make sense? Multiplied by xi, that is a value for an individual parameter that we're putting in. Let's say that is let's say that's square footage or something. One, right? And the one denotes which feature I am considering. In the plot we only had one feature, right? That was the square footage of the house. But I could also have a pool. The pool does affect the price of my house. So I could write that as plus theta 2, that's a parameter that I need to obtain, times my data point for that individual home, right, times my second feature that I am considering. Does that make sense? All right. So this can go on forever, and maybe the second feature is size of pool. Plus, that can go on forever till you get to theta y x of I m for all the features you want, right? Now, this gets you exactly what yi should be, but that's never what, well, should be what you want it to be, right? That's never how this works. So we have to add plus e, right? We have to add an error term to this because there's always going to be some error in our models. So this expression here is what we're trying to build for kind of a multi-parameter linear regression. What we're going to plot in the class is just a one parameter regression, right? So here you have feature 1 versus feature 2. Typically, this will be y, and that will be x, but you can have multiple linear regression kind of in a multiple domain, and this is how you build out that equation. That equation is incredibly detailed, but we like simpler ways to write things. So we're just going to write this as y, which is a matrix, x, which is a matrix, theta, well, actually y is a vector, I take that back, theta is a vector, plus e, and x is a matrix, right? And so we have our target, we have a vector of our targets is equal to our data set times a vector of all of our parameters that we train plus a good chunk of error. And we can draw this out as x is equal to x11, x12, that goes all the way out to x1m, x21 all the way down to xn1, and so this would be x22 all the way down to xn2, right? And this comes all the way down to xnm. And that is all of our data for all of our features, right? For multiple instances, for multiple eyes, and for multiple features, right? So size of your pool, your screened-in porch, the number of fireplaces, all of that. For each one of those, we need a theta which is equal to theta 1, theta 2, theta p. Right, and that's just kind of the number of thetas that we have, and this is what we're trying to obtain. This is what we want to spend millions of dollars and lots of money, is to attain these parameters that change in our model. And y is equal to y1, y2, yn. And those are going to be the actual prices of the houses that people paid, right? Those are not hats, those are actual prices. Okay. Can you model air? This is a great, I love, okay, this is awesome. This is great because this tells me I can model my air, or I have to know my air. But can you model air? No, not really, right? So we have to make an assumption. We have to drop the air term because I don't know what the air is, and so I can't optimize around an unknown air value, right? So therefore, if I drop that, it becomes kind of dropping the air term. The best that I can reasonably do is y hat is equal to x. I know x. X is my data. Granted, my data may be wrong or bad, but I have it. Theta hat. So now instead of actually knowing my best parameters, I'm going to estimate my best parameters. And so our goal is to find an estimation for the best parameters that we can get. So the goal is to find theta hat such that the air is minimized. Mathematically, it's simple enough to say that, right? We want to minimize it on our hyperplane. And we are given this wonderful expression from that equation above. We just move some things around. Theta hat is equal to x transpose x inverse x transpose y. And this is our normal equation. And considers and is a closed form solution. Does that make sense? So that is our normal equation and is a closed form solution.